Hello, my name is Michael Lindner, and I'm a student in the physics department here at UW working with Dr. Amal Alwahish on research into the proton dynamics of strontium hydrogen phosphate. SrHPO4 is a member of the alkaline earth phosphate family, which are candidates solid electrolytes for proton-conducting solid oxide fuel cells. The development of solid oxide fuel cell alternatives to fossil fuel-based energy cells calls for suitable materials capable of high proton transport at temperatures below 773 Kelvin. Strontium hydrogen phosphate could fill this role, but its proton mobility has not previously been reported. Therefore, the question that we are trying to answer is, what is the nature of proton conductivity in strontium hydrogen phosphate? Determining proton conductivity may be accomplished by studying the diffusive motion of protons in condensed matter through a technique called quasi-elastic neutron scattering, or QENS. QENS experiments involve a beam of neutrons that are scattered of the nuclei of a bulk sample and into detectors, from whence properties about the change in momentum can be used to deduce the diffusive motions. Proton diffusion gives a particularly strong signal, and thus strontium hydrogen phosphate is well suited for this experiment. The primary signal from QENS, called intensity, is measured in arbitrary units and is known as a scattering function. The scattering function usually takes on the form of a Lorentzian, and so various physical models of the diffusion are fit to the half-width at half maxima of the Lorentzian. An ideal result for proton conductivity in a candidate material would be a long-range diffusive process, which would look like a linear relationship between the half-width maximum and Q squared, with Q having units of inverse energy and being the quantity with which our data is binned. Using the Data Analysis and Visualization Environment, or DAVE software, being produced by NIST, we see through our preliminary analysis a definite temperature dependence in Q squared versus the half maximum of our data. High temperatures in our data cannot be fit linearly, but there are other kinds of diffusion and therefore other models that we can use to fit our data, such as the Chudley-Elliott model. We also compared our analysis to that of a different material, monatite or SrHPO4. The scattering behavior is very different in our material to that of monatite. Monatite also displays a temperature dependence, but unlike in strontium hydrogen phosphate, its dependence on Q squared remains relatively flat until much higher temperatures. This leads us to hypothesize that it is unlikely that strontium hydrogen phosphate undergoes long-range diffusion at high temperatures. Calculating the diffusion coefficient by fitting them into a diffusion model such as the Chudley-Elliott model will be the next step in our research. Strontium hydrogen phosphate is chemically stable in our temperature range, so this kind of analysis would be perfect for understanding more about the temperature dependence of proton diffusion in strontium hydrogen phosphate. Thank you for your time, stay healthy, and enjoy the rest of the symposium.